It's our pleasure tonight to have Andy Buchanan speak to us. Andy is a Professor of Structural Engineering, Professor Emeritus these days, after a long career at the University of Canterbury. I'll confess at this outset that I'm a structural engineer by profession, and Andy's one of Andy's books, The Timber Design Guide, I suspect has a copy in every structural engineering office in New Zealand, certainly all the ones I've worked at. So he's, although I didn't study under him at Canterbury, he's a very well-known figure in structural engineering circles in New Zealand. I thought it would be great to just take the opportunity to play a 2-minute video, which just summarizes some of the recent work he's done, and probably gives you a good background leading into his topics today. So bear with me and I'll play that video now.
Professor Andy Buchanan from the University of Canterbury is a world-leading researcher in the use of timber in earthquake-resistant buildings.
10 years ago, when we were doing earthquake engineering research, we realised that we had to somehow come up with a way of designing buildings that wouldn't be damaged after the earthquake. And the concrete people were doing it, the steel people were doing it, and we said, let's try it in wood. And the whole idea was this: if we have an earthquake and the building gets shaken about, it snaps right back to where it started.
Well, I've been lucky enough to travel overseas with Andy to Canada and Japan, which are both wood-centric economy, and also they've got a very severe earthquake problem. And he's a world guru, basically.
We got $5 million of industry money. We went to the government, they matched that money, and we then had a R&D program which has resulted in buildings like this. It's a renewable resource, it's sustainable, it's lightweight, it's strong. In terms of earthquake performance, or fire safety, or cost, wood can match steel or concrete. But in addition to that, we've got the low energy and the low carbon footprint of the wood buildings.
Working with industry from day one, Professor Buchanan is creating technologies that will change the way timber is used in construction around the world.
The university got involved because it could immediately see that there was commercial potential out of research.
The world is watching what's happening here in New Zealand. Timber buildings used to be thought of as 2-3-story buildings. Now there are 5-6-story buildings. There's a 10-story building just been finished in Australia, even 30-story buildings in wood. There's this enormous demand for tall timber buildings around the world for reasons of sustainability and renewability and low carbon. But what the world doesn't have is a way of making these buildings earthquake-proof. So that's what we've got.
Technology is so good it'll become a worldwide phenomenon. It's a perfect example of what can be done with clever scientists at a university, aided with a commercialisation function, meeting a market need.
So moving on from Andy's career at the university, he's since gone back into commercial practice, and I've certainly appreciated the sort of case studies and fantastic examples that have been coming out from his business in recent years since that video was shot. So without further ado, I'll hand over to Andy to bring his presentation. Thanks, Andy.
Let's go, guys. First of all, thanks very much to ESR for inviting me on. I've been a member of ESR for many years, but rather a passive member. But it's a pleasure to be here tonight to talk about a story, really, about the carbon benefits of timber buildings. And as Brendan said, I've been a structural engineer for many years. I got interested in wood partway through that journey, and to start with, wood engineering, timber engineering was structural engineering, but we had to deal with problems of fires and then earthquakes. But what's the big driver for timber buildings right now is climate. So let's move on. If we think about climate action. You know all this. There's enormous pressure on us to reduce carbon dioxide emissions, and the only way to do that is to phase out fossil fuels. Of course, we can plant a few trees to offset, but that doesn't solve the problem. We have to stop using fossil fuels, and we've got to move to a low carbon economy. And the thrust of this talk is using low carbon buildings as part of that low carbon economy. And I'm going to quantify all of this, and let's see where we go. So what I'm really talking about is very simple. We're just talking about using wood instead of concrete or steel. And what we want to be able to do is to make buildings which have got zero embodied carbon. So I'm really just talking about embodied carbon, which is the carbon consequences of producing the building materials. And so this little building you can see there, I'll give a little case study of that later, but that's the St Albans Community Centre in Christchurch. And there is the carbon sequestered in the wood, or stored in the wood, more than offsets all the carbon emissions from making the other materials. So let's go ahead. As I said, I'm now talking about embodied carbon emissions using low carbon materials. And there are two parts to it, because there's what we might call the storage effect, or the biologists talk about carbon sequestration or sequestered carbon. And that's the carbon which is stored in the building materials. In addition to that, there's another benefit, which is what I call the substitution effect, because if we use wood instead of steel or concrete, well, then we have substituted, and that means another contribution that hasn't come through. And so I'll talk more about that in the future as we go on. Now, of course, in terms of the carbon footprint of a building, the embodied carbon is something which happens when the building is built, and it's there as long as the building exists. But in addition to that, there are the operational carbon emissions for the whole lifetime of the building. And I'm not looking at those now. What I'm doing in this talk is I'm only looking at embodied carbon, but I have to acknowledge that if we want to have low carbon buildings, we've got to go to a lot of effort to provide thermal insulation and manage the energy so that we reduce those emissions as well. And of course, that can be done with passive houses and other such technology. So let's just think about trees for a minute. This is a photo of a forest, which I'm a part owner of up in Marlborough. And the carbon is stored in the wood for hundreds of years. And so when we're looking at planting trees to offset carbon, the only thing we're doing really is we're looking for the wood in the trees, because it's the wood in the trees in that forest that have offset carbon emissions from elsewhere. Of course, the forest is absorbing carbon dioxide every day and pumping out oxygen, but the increase of carbon on the ground is only coming from the increased amount of wood and the increased size of the trees. The carbon lasts for hundreds of years. You all know this building, the old government buildings in Wellington, is 150 years old, and the carbon in that wood is still there, just as it was when the building was built. Let's just have a few numbers on this. Dry wood is 50% carbon. Of course, wood is a complex organic material. It's made up of cellulose and hemicellulose and lignin. Those are all organic compounds, but half of it is carbon. And a cubic meter of dry wood weighs half a ton, 500 kilograms. And half of that means that it stores 250 kilograms of carbon, C. Now, carbon accounting around the world now is not done in terms of tons of carbon. It's done in terms of tons of carbon dioxide equivalent. So we've got to take the 250 and we've got to multiply by 44/12, and because the atomic weight of carbon is 12 and the atomic weight of oxygen is 16, and so CO2 is 44 and C is 12. And so this is a simple calculation, but some people who are doing calculations of carbon offset forget to do this. So it means that the 250 tons of carbon in a cubic meter of wood is about 920 kilograms of carbon dioxide equivalent. So 1 cubic meter of wood offsets about 1 ton of carbon dioxide. And that's the sum that gets done. When you buy your Air New Zealand ticket and you tick the box for a carbon offset, that's the people behind the scenes are making this calculation and figuring out how many tons of carbon dioxide are emitted from your flight to Queenstown, and they then use that to figure out how many trees they have to plant. That's how it works. Okay, let's look at some new technology. Wood, we're looking at mass timber, large lumps of wood, like glued laminated timber, big lumps glued together. It's been around for a while. Laminated veneer lumber has been around for 20 years or so, and we've got 3 factories in New Zealand making LVL, laminated veneer lumber. Carter Holt Harvey, Marsden Point, and Nelson Pine Industries in Nelson, and Duke and Nishu in Masterton. So that's to make things that are long and strong. But the new boy on the block is cross-laminated timber. And cross-laminated timber is like thick plywood. There's all a bit like plywood, because LVL is like thin layers. It's like plywood with all the veneers, all the grain running in the same direction. CLT is like thick plywood because it's not made of thin layers, it's made of 4x2s laid on edge. But they're alternating layers, and so it's for good, perfect thing for great big panels. Just something that's going to come up again later. To make any of these products now, to do it economically, it requires a big investment, because if it's all done by hand, it's so expensive it won't happen. But companies who are making these products now they're all robotic, and it requires a lot of money to get going. Just to say a little bit more about cross-laminated timber, you can see in the picture there, there's a 3-ply and a 5-ply. And the 3-ply would be used wherever possible, but the 5-ply, and you can make a 7-ply. And that 3-ply is about 100 millimeters thick. The 5-ply is 120, 150, depending on the layers. This CLT was invented in Europe in the 1990s. And in 2012, Robin Jack set up XLAM in Nelson, which was started to become successful. Then they were bought out by Hine Timber in Australia, who closed down the Nelson factory. So XLAM are now in Australia at Albury, Wodonga. I took that photograph in their factory just last month. But the new boys on the block are Red Stag in Rotorua, and last year they completed their factory and they're gearing up now. And so we have 2 big factories in Australasia, with some more on the way in Australia. There's new factories coming in Adelaide and Perth. So that's a product I'll be talking quite a lot about. I'll just, by way of background, as Brendan mentioned, back from between 2008 and 2013, before I left the university, we had a company called STIC, the Structural Timber Research Consortium, which brought together research at Canterbury and Auckland and Sydney, and that's where we developed this press lamp system that you've seen, and which has got an important place for seismic design of timber buildings, but not for all timber buildings. You don't need that, but it does, the technology's there if we need it. The first building using that technology was the NMIT, Nelson Marlborough Institute of Technology building in Nelson, opened in 2010. And that was built back in the days when Jim Anderton was Minister of Forestry. Remember Jim Anderton? And he was very much in favour of promoting timber buildings. And this building got $1 million subsidy from the government because of the new technology. That was the post-tensioned or press lam walls being erected, and that's the finished building today. It's a lovely building. So let's get on to the topic. The topic is, what are the carbon benefits of building more timber buildings in New Zealand? That's the question. There's a bit going on in the background because MBIE has a Building for Climate Change division, and they have a whole of life embodied carbon emissions reduction framework, which is, and as you note, it's whole of life, and also embodied, and they're working to reduce emissions from buildings during their construction. And I've been talking to them a bit, and they became aware of a paper which I'd written 20 years ago, 1999, wood-based building materials and atmospheric carbon emissions, which I wrote with a co-author, an American student, Bree Levine. And we published that, and it went under the radar at the time because no one was much interested. But now it's come up again, and the Ministry of Primary Industries, the Forest Service people asked me if I could update that. So I've done that for them, and that's what this talk is all about. And the report I wrote for them was published last week in the latest journal from the New Zealand Timber Design Society. So there are copies out there, and I can make them available if you want a written report. But let's get on with the show. Back in the stick days, we started looking at buildings, and this was a new building, a concrete building under construction at the University of Canterbury 10, 15 years ago now. But what we did with that concrete building, we had all the numbers, quantities, and we did 3 new designs. We designed a steel alternative and a timber alternative and something special we called the Timber Plus alternative. And if we compare those 4 options, this is what it looks like. And this is looking at the embodied carbon dioxide in all of the building materials. And so we've got a graph like this. We've got the concrete building, the steel building, the timber building, and the Timber Plus building. And the vertical axis is tons of carbon dioxide. And that blue color is concrete, most in the concrete building, less in the others. The red color is steel, most in the steel building, as you'd expect. What's the yellow? Well, the yellow for this building was the aluminium window frames and the whole aluminium facade. It was huge. And that's why, after doing this, we thought, well, there's got to be a better way. So that's when we moved to the Timber Plus, and we said, let's get away from the aluminium and let's look at timber, wood for window frames. And the wood is the negative item here because that sequestered carbon is a negative emission. And if we simplify that, we can just look at the net values, and you can see here there's your concrete, steel, timber, and the Timber Plus building. And so if there's enough wood in the building, we end up with carbon 0 or even negative. And so that's what we did for one building. Net zero embodied carbon is possible. And in that case, the sequestered carbon or the stored carbon in the wood offsets the CO2 emissions from making all the other building materials, including the glass in the windows and the jib and the wall lining and the corrugated iron on the roof, and in that case, the reinforced concrete foundations. So that's an old story. I'm now going into the procedure that I went through 20 years ago, and I've just gone through it again, and it's quite a few. There's a lot of steps in this, and there's a lot of accounting, and so I'm going to put up a lot of spreadsheets and show a lot of numbers, but I won't dwell on them too much, but because we want to get out the other end. But what we wanted to do is we went to Statistics New Zealand to find the total number of new buildings in New Zealand in 2019, which was the latest year we had the data for. And then we split those into broad categories of use, as you'll see: residential, commercial, industrial, farm buildings. And for each one of those categories, we did some guesswork. We estimated, we guessed roughly what is the percentage of structural steel and concrete and timber in the structure of those buildings. And on the basis of that, we knew the floor area, so we could calculate the volumes of structural steel and concrete and timber. And then what we did was to propose a new mix of structural materials. I'll describe this all in a bit more detail, but these are the steps. which meant we then recalculated the volume of materials. And then we took the carbon coefficients for each material, because there's information out there on how many tons of CO2 are emitted when you produce a cubic meter of concrete or a ton of steel. And using all those numbers, we could calculate the total CO2 equivalent emissions for all the buildings built in New Zealand in 2019. And then to finish off, we had to calculate how much wood we would need to do all of that, making that change from steel and concrete to wood. So that's what we're going to do now. We're going to work through those steps. There are some limitations, quite a lot. This is not a full life cycle assessment, an LCA. Absolutely not. That would be a much bigger job. We have not included the operational emissions. We have not included the construction and transport energy, and we have not included the end-of-life options. So this is only looking at the structural materials. It's a little different from that previous study I looked at where we included all the materials. This time around, we've made the assumption that the facade of the building, the roofing on the building, the internal fit out is going to be the same in whether the building structure is concrete or steel or wood. And to keep things simple, we've also assumed that there's no change to the concrete foundations. So when I'm suggesting moving from a concrete office building to a timber office building, the materials I'm looking at are only the superstructure above the ground. Of course, there would be savings due to changing lightweight and so on. The exception to that is house slabs, house foundations, and you'll see why. So those are the limitations. So these are the categories. I took all of the buildings in New Zealand and we just broke them down into houses and apartment type buildings, which is apartments, townhouses, retirement homes, hostels, motels, and then office, education, commercial buildings, which includes healthcare, shops, schools, hospitality, all those kinds of buildings, and then factories and storage buildings and farm buildings. So the only way to do this guesstimate is to break it down. So this whole exercise is a big picture, a high level, big picture guesstimate of what would happen. Because there's a lot of estimation in here, but we have to do these things to see whether it's worth proceeding. Okay, you're going to see these 5 categories again and again in the next few slides. So the 2019 figures, those are the 5 categories which I split them into, and you can see here the number and the floor, the value and the floor area. So in 2019, there were 21,000 houses built and 12,000 apartment style buildings and 1,400 office and so on. And the value, you can see the numbers there, but the number we're most interested in are the floor areas, because what I've done, the other thing I've done in this study is I've just assumed that next year and the year after, we will build the same number of buildings as we built in 2019. So there's all kinds of assumptions in here, but you have to do it if you want to make progress. So those are the floor areas. Then the structural materials. Now it starts to get a bit more detailed and a bit more interesting. And these are the guesstimates I talked about, because if I just go back again, that data there is all data from Statistics New Zealand. There's no guesswork there. I've just taken their tables. But we go to the next slide. Now I'm starting to make some estimates. So the same 5 categories. And if we look at house foundations, for example, I've just gone out to the industry and talked to engineers and builders that I know. And roughly speaking, in 2019, let's say 90% of houses were concrete slab on grade, and 10% were some type of timber construction, a pole house or a light timber frame elevated style. So that's an estimate. And the same thing for apartment buildings. That's much more difficult, but I watch these going up right now in Christchurch. There are tilt panel and concrete masonry apartments, and there are light timber frame apartments. So 50-50. And for office, commercial, educational buildings, 50-50. In the Christchurch rebuild, I'd say it's more like 75% steel and 25% concrete, a huge number of steel buildings. But over the country, I've said 50-50. Factory and storage buildings, they're all made of steel, portal frames. Farm buildings, something like that, guesstimate again, mostly steel, some timber framing. So those are the starting numbers. Now I'm going to put up another column here, which are the possible future materials. And so here I'm saying for the house foundations, let's say that we could cut the concrete slab down to half, and let's start using mass timber or light timber framing for those, 50-50. For apartments, let's say we stop using concrete and we make them all in timber. And for commercial office buildings, instead of 50-50, let's cut that in half and go to half timber. For factories and storage buildings, let's again half timber, and a bit the same with farm buildings. So you can argue with these numbers. These are what-if numbers, but they're the numbers that give us the answers. So just as an example, most houses in Christchurch are built on something like that, rib raft, something like that, where the concrete is finished. Concrete actually is the biggest problem because the cement and concrete industry is responsible for close to 10% of the global CO2 emissions, maybe 8%, 8, 9, 10. It's 3 times more than emissions from air travel, for example. It's huge. And concrete is great stuff. It's wonderful stuff. And there's a lot of work going on looking at trying to come up with low carbon concrete, but with great difficulty. But my suggestion, and for houses, if I was building a new house right now, I'd do something like this. Timber poles driven into the ground, no concrete at all, and timber beams bearers and cross-laminated timber, CLT floor slabs. Why not do it like that? For apartment buildings, we see these buildings going up all over the country. We don't have to do that. This is a lovely CLT building, which we helped the design with in Sydney. There are more of these in Sydney than there are in Australia than New Zealand right now, but they're coming, and they're coming fast. So a building like that, all the structure of that are those cross-laminated timbered walls, and that's the finished building. Lovely building. It'll be there for hundreds of years. And here's another building we've just done recently in Wellington, the Mary Potter apartment buildings, which looks like that. So there's no reason we can't do it. For commercial office buildings, this is a recent building, and University of Canterbury built the Beatrice Tinsley building with, it's all, that frame you can see there is all LVL, laminated veneer lumber, and the floor cassettes are LVL rather than CLT, and that's the finished building. Trimble Navigation building in Christchurch after the earthquake, that's the structural frame, that's the finished building. Enough of that. Factories, that's, as you know, nearly all industrial buildings look like that with steel portal frames, but there's no reason they can't be done in timber. And farm buildings, that's what we see, and there's no reason they can't be done like that, and a lot are being done like that. So those are the sorts of examples that I had when I made those previous assumptions. So we're right back to our overview, and we've calculated, we're down to number 6. We've proposed a new mix, and we've calculated the volumes of materials. So we've still got 3 more steps to do to get to the answer. So let's keep going. In terms of carbon coefficients, we have numbers like this, where for the materials I'm talking about, so I'm talking about sawn timber or engineered timber. By engineered timber, we mean glulam, LVL, CLT. They're all about the same. And we've got units, and you'll see the units are a bit different, and we've got the quantity. And the numbers that we've got here are mostly coming from documents called EPDs. And EPD is an environmental product declaration. And luckily, because for a while it was a mess, but now there are international standards for EPDs, and all of the main manufacturers of structural materials in New Zealand have produced environmental product declarations, which one of the outputs of that is that the carbon emissions, the embodied carbon in the manufacturing of the material. The EPDs do much more than that. They look at a whole range of environmental impacts of the material, but I'm only looking for one number there. Those have been summarized in a chapter of the New Zealand NZ Wood Design Guide, which you can get online very easily. And the other place where you can get this stuff, which I would recommend as being the easiest way to make these calculations, is go to the Naylor Love website, and there's a free access to a calculator on there where you can do for one building on there what I've done for thousands of buildings. So let's carry on here. What we see here is that for the timber, we've got the green numbers, which are negative values. So that's stored carbon, sequestered carbon. And for concrete and steel reinforcing, they're all positive numbers. The numbers can't be compared very easily because the units are different. For example, you can see there for concrete, it's a cubic meter of concrete. You remember me saying before, a cubic meter of wood resulted in about a ton of CO2 emissions being stored. You can see from this, if you multiply by 3 to get to 3 of those would be, sorry, a cubic meter of concrete results in 343 kilograms, or a third of a ton of CO2 emissions. So you can compare those. I won't say any more about that, but the steel numbers are much less because the quantity surveyors measure steel in kilograms and tons, not in cubic meters. So we're looking at kilograms of CO2 per kilogram of steel. So all I'm going to say here is that those numbers are not my numbers. They've come from elsewhere. So what I'm going to do now is I'm going to combine those numbers with my building quantities. So let's just look at office buildings. So if we look at office buildings, I now can come up with a table like this, where for the office buildings, I can look at the concrete office building, a steel office building, a light timber frame office building, or an engineered timber office building. And across the top, I've got these materials. And what these numbers tell me how much concrete there is in a concrete building. So if we look at concrete in a concrete building, there's about 0.2 of a cubic meter of concrete per square meter of floor area. And in a steel building, there's about 8 kilograms of steel per square meter of floor area. But then if that building was not a concrete building, but it was a steel building, you can see how the numbers change. And those are numbers. The way I got those is I went to a friendly quantity surveyor, and a number of them and a number of builders, and I got quantities for a number of typical buildings, and we had to work those numbers out. And having done that, we then went, well, I've just showed those. What we then did was we took the carbon coefficients from the previous slide and we multiplied the whole thing up. And so for a steel building, for example, we took, there's 0.12 cubic meters of concrete per square meter at 343 kilograms of CO2 emissions per cubic meter, and multiplied those together. And then for the structural steel, we multiplied those two numbers together. And for the steel reinforcing, we multiplied those two numbers together. And for the steel deck, the com floor, we multiplied those two together. And we added up the middle row. And what did we end up with? 359. What's that number? What that means is, for a steel office building, a typical steel office building of the sort being built in Christchurch after the rebuild, there's about the carbon emissions are 359 kilograms of carbon dioxide for each square meter of that building. And if it was a concrete building, it's a bit less, it's 256. kilograms of carbon per square meter. I've got light timber frame in there, but we're not doing light timber frame buildings, forget that. But if we had the timber building, in the timber building, we'd use about 0.25, about a quarter of a cubic meter per square meter. If you think about that, it means that it's equivalent to a floor slab 250 millimeters thick. Of course, all the wood's not in the floor slab, half of it's in the beams and columns, but the number makes sense. And if you add the carbon coefficient of 32 kilograms of carbon, sorry, we're back to engineered timber, the 0.6, the 665, then you get those numbers. Okay, let me keep going. This is all accounting. And we repeated that for each material option for all 5 building categories, and we got some answers. Okay, what are the answers? Well, it looks like this. So what I've got here, the same 5 categories for 2019, and the numbers now are how many thousand tons of carbon dioxide emissions from building all of the houses that were built in New Zealand in 2019, and all of the apartments, and all of the commercial office buildings, and all of the factory buildings, and all of the farm buildings. And the total is 859,000 tons. And then we compared that with the what if we used less concrete and less steel and more wood, what would we come up with? It would come up to being a negative number. And if we look at the difference between those 2 columns, we end up with these numbers. And so the number on the bottom right, 1,024, that's the finished number, because what that means is if we made all these changes to all these buildings using these numbers we've got, we would have a reduction of 1 megaton of carbon dioxide in the New Zealand economy during that year. And it's not a huge number, but it's not a bad number. It's about 2.5% of the total fossil fuel emissions of 39.5 megatons of CO2. I haven't put methane in here. I don't want to get involved in that argument. But so it's one, just got that number. So that's quite a big number. And the biggest contribution here is actually from apartment buildings with CLT floors and walls using CLT and light timber framing. And at the current market price, it's actually more like 80, but it's been hovering around 50. If it was $50 a ton, the value of this reduction is about $50 million. And half of this benefit comes from storage of carbon in the wood, which is the sequestration effect, and the other half comes from the reduced carbon emissions from not making steel and concrete. So there we go. Now there's one more thing we want to do. We want to see how much wood is involved. So this is how much extra wood we would need in each of these categories. And you can see here, I've divided this up into sawn timber and CLT, LVL, and plywood. And we've come up with some numbers down the bottom here. And we add those numbers up, and the total, so we would need an additional 650,000 cubic meters of wood products to make this change that we're talking about. What does that number mean? Well, because when you turn logs into manufactured wood, you lose half the wood, goes into sawdust and fuel and stuff like that. So we'd need an extra 1.3 million cubic meters of logs. And that's only 8% of the current New Zealand usage. Or another way of looking at it, if you look at those piles of logs being exported at the wharves and all over the country, we'd have to retain 6% of that in New Zealand to make these changes that I'm talking about. Doesn't sound like very much. But the biggest hurdle actually, or one of the big hurdles, is processing capacity, because we would have to have processing capacity to saw and manufacture and treat and process 650,000 cubic meters. And that's about 10 times the size of the new Red Stag CLT factory in Rotorua. And I don't know how much that's cost, but it's cost a lot of money, and it's taken quite a few years from woe to go. So that is actually the biggest hurdle in the whole thing. Just a little case study. I'll go back to St Albans again, because it's a favourite building of mine. If you're in Christchurch, go and have a look at it. It's open every day. That's the building being built with Daniel and Emma, the PTL engineers, of the walls being stood up. And that's Leanne Dalzell, the Christchurch mayor, opening the building. And at the opening, I hadn't done my homework before, because I asked her, I said, you didn't say anything about the carbon. She said, nobody told me what to say. So I said, well, here's the carbon story on this, which I've since worked out. It was very easy. The CLT, there's a huge amount of wood in this building, 150 tons, 300 cubic meters. There's 180 tons of CO2 sequestered in that one building. And I said to Leanne, that would be 1 million kilometers of your personal car driving that would be offset by building this one building in wood. So that's a nice little story. So the conclusions are simply these. If about half of new buildings used wood instead of concrete and steel, houses, apartments, schools, offices, factories, farm buildings, we would have about 1 million ton reduction in CO2 emissions, which is about 2.5% of the national CO2 emissions. And I read in yesterday's paper that internationally, airline travel globally is 2.5% of CO2 emissions. And I look up Air New Zealand, that looks about 3%. So what we're talking about really is, if we did all of this, that would be equivalent to shutting down the New Zealand airline industry. Not that I want to do that, but that's what it means. And the extra wood would be 6% of log exports, which is 10 new red stag factories. It's a big task, but it could be done. That's all. Thank you. I'll stop sharing, Brendan.
Excellent. Thanks very much, Andy. That was a fascinating talk, and I'm very interested to see what discussion and questions it brings up. I might just start off. There was a question in the chat just related to some of the figures you presented around concrete floors and that sort of thing. In your tables, you looked at house floors for residential, or foundations, I think it was. Could you just comment on the distinction between looking at just the foundations or the rest of the building, or what the thinking was on that point?
Yes, yeah. Look, the assumptions in there were not always easy, because especially I wanted to keep it simple and not get too complicated. And so what I was sort of assuming, you might say, is that I'm assuming with houses that they're single story, and we can just replace the concrete slab with a light timber frame floor or the CLT floor of the picture I showed you. When it comes to apartments and apartment type of buildings, which includes all of the hotels and motels and all those buildings, I'm assuming that they're all several floors, because I've just left I'm only looking at the upper floors. I'm not looking at the ground floor. And the same with the commercial office buildings. I've just assumed that the floor slab and the foundations are unchanged. So I think that's the question.
Thanks, Andy. Another question here on the chat. Just looking for your comment on what the government's doing to support growth in timber buildings.
Well, they're doing quite a lot, actually, because they've got this Building for Climate Change section in MBIE, and there's quite a lot going on. At the moment, they're just investigating options, but there've been discussion documents produced, and if the discussion documents, if the proposals are accepted, the intention is that in the medium to near future, in order to obtain a building consent, you'll have to have done some sums, and first of all, not to have a cap, but just to have done the calculations to show how much embodied carbon is in your building. And then they're trying to come up with some sort of a cap so that you wouldn't get a building consent unless you had a cap. But politically it's quite difficult, and it is happening. One other thing that's happening, I'll just mention, because in terms of government, is that Waka Kotahi, Transit New Zealand, now have a program to look at using wood, engineered wood, for main road highway bridges. And that is moving quite seriously. And we've been, in my consulting through PTL, we've been helping them with that. And they're talking to some of the big boys in the bridge consultants, and watch this space. Things are happening.
There's a couple of questions on the chat also just around costs. So comparing costs of the types of timber construction you've talked about with the conventional construction. Do you want to make any comments on the impact that cost might have on your envisioned future?
Yep, of course we have to think about that, no question. And we have a lot of timber buildings coming through our office, and there are people listening who might be able to answer this more clearly than me. But in most cases, there is not much difference. There may be a small cost penalty in the structure, because I'm only talking about the structure here. And but it's not a big deal. I mean, in many cases, the material cost will be offset by the rapid construction and savings in foundations. And even if it isn't, even if it's a 10% cost increase on the structure, I mean, that's only a 2% increase in the overall cost of the building, because the structure is only a quarter of the total cost of the building. So the cost implications are not significant. The biggest problem, as I say, is the manufacturing capability.
Andy, may I comment on that?
Yes.
As you know, I'm developing a carbon and cost tool for residential construction. And you're exactly right. But a couple of things are that the operational carbon versus the embodied carbon starts to tip the balance. And an easy example, it's not in structure, but is in insulation. You know, if you're just looking at embodied carbon, you better not to put any insulation in. But as soon as you start to put in operational carbon, the whole balance tips over time. One of the bizarre things, and you alluded to this before, I'd love to know more about what you did. An excellent presentation, thank you. Is that, yeah, timber joinery, windows and so on, are generally a lot more expensive than aluminium. That always strikes me as bizarre in a country like ours. But I think that is a case where you do pay a premium to suck down the carbon content. I won't say any more at this stage. Thank you. Really enjoyed your presentation.
Yeah, well, thanks, Lindsay. But it may have been a little bit confusing, because in the prelim, I talked about that University of Canterbury building where we looked at all the building materials, including the facade. But this exercise that I've just done is only looking at the structural materials. So I'm assuming that the facade is the same, and I think there's a big opportunity there in the facade business. But of course, there are lots of other questions, because there's, you know, facades, the questions about thermal performance and fire safety and so
on. I'm also interested in the whole business of the windows and joinery, and because my impression is to have good quality wooden joinery, it's typically pretty fancy stuff like imported Western red cedar or some kind of other material. And I wonder about the practicalities of doing it here in New Zealand with our resources.
Yes, well, I'm not an expert on that, but what you say is quite right, because of all those timber quantities I'm talking about, another 1 million cubic meters of wood, if this were to happen, that's all radiata pine. And radiata pine, it's not the world's best wood, but it's bloody good stuff. And it does have has many advantages, but it's not good joinery timber. If we were to start making window frames and facades, we need a much more stable product. Of course, peeling it and gluing it back together gives it stability. That's why LVL is so popular. House builders like using LVL studs because they're stable, they don't move. But at the same time, if they're exposed to the weather, they've also got to be treated. And so that's all I will say, is that it's not that simple. And so I'm not pushing wooden window frames very hard, but I think there is an opportunity there, and it might be using imported wood. Or if we get to the day when we start carbon farming totara in Northland, and we have huge quantities of farmed totara or other species like that which might come on stream, who knows?
Thank you.
Andy, I might steer the questions a little bit for a moment to the issue of life cycle assessment. So your talk was specifically focused on the embodied carbon of building the building and the equation of carbon neutrality or perhaps carbon savings from the embodied carbon in sourcing all those materials and putting them together into a building. And it's a bit of a no-brainer that's a sensible idea, pretty compelling. However, when I take that sensible idea and plug it into a life cycle carbon calculator, with the international rules, they don't let you count often timber that's in a building as being truly sequestered, because they say, well, one day it's going to come out. So I guess one answer to that you've given is that, you know, if we design the buildings right, they can be up there for hundreds of years. That certainly buys us a lot more time than we've got at the moment. But it seems like there's a bit of a question mark about how to deal with the timber at the end of a building life. Have you heard of anyone discussing that question for New Zealand and what that might look like in the future?
Yes, absolutely. When I was at the university, this question came up a lot. And I can see that one of the listeners here is Robert Finch. Hi, Robert, who was the chief executive of Stick when we had the Stick company running. And he's got a new job now. He's now the director of the New Zealand Timber Design Centre, which has just been set up in the last few months with some government money, with the intention of promoting timber buildings. That's another thing the government is doing. And last time I talked to Robert, he said, we've really got to have another look at this end of life question, which we have done. But it's a tricky thing, Brendan, because in the short term, I would say the carbon crisis is a right now crisis. And if we're going to penalize wood because we don't know what's going to happen to it in 100 years' time, and we do nothing accordingly, we get nowhere. We've got to get on with the job and do things. And the point you make is that and I'm not entirely up to date with the latest rules on this, but for a while, when you asked the LCA people, they said, well, even if we don't know what's going to happen to the wood in 100 years' time, we assume that what will happen to it then is what happens to it now. And it goes to a landfill. And in fact, if wood does go to a landfill, that's a good thing because it gets buried and the wood lasts in a landfill for thousands of years. The carbon stays there. But on the other hand, landfills are not politically correct. Nobody wants landfills. And so we've got to look at other things. And there's a hell of a lot going on. People are looking at first of all, you can burn it, and you can burn it take it up to Marsden Point and burn it in some of the peeler cores from Carter Holt Harvey, I understand, are being used for fuel along with used car tyres and Golden Bay's cement kiln at Marsden Point. I could be corrected on that, but I think that's the case. So there's lots of things you can do with it. So the end of life is not a showstopper. That's what I'm saying, Brendan.
Any other questions from the floor?
Can I ask a follow-on question to that, please? Another dimension of end of life, Andy, is deliberately building for deconstruction and reuse of components, the sort of buildings as materials banks concept. I know there's always limitations on standardization of components, but it does seem to me that timber components especially might lend themselves to good deconstruction and therefore enhancing further the potential reuse. Do you have any comments on that aspect of it, especially in heavy timber engineering?
Yeah, look, I agree entirely with that. I mean, one of the obstacles to building big buildings in wood are the connections. And it's simple because steel, you can weld it. And concrete, it's a liquid, you pour it into a mold. And with wood, you just get what you start with, which are big, strong sticks or big flat panels, and you've got to connect them together. And so the structural engineers listening to this, they'll at least half of the time and effort involved in designing a timber building goes into the connections. And if the connections are easily done correctly, then they can be taken apart just as well as they can be put together, which gives you components. So there's all kinds of potential, but I'd have to say that most building clients are not asking for any extra effort to go in terms of thinking about reusing their building. We did it at the university with the test building we built at the university, which was a 2/3 scale building, which went through a shaking table, and that became Robert Finch's office. As some of you would have seen that building, and it was because it was all taken down and put back together, and it's since been taken down, and it was supposed to be put up together, but I think it's still sitting in a container somewhere waiting to be put back together. So it's a good point. No problem.
Thank you. Good answer.
Andy, I had one question on the processing capacity issue that you mentioned as one key constraint if New Zealand wanted to build more buildings with structural timber. It seems to me at the moment you've got MB signalling that they're going to put a emissions cap per square metre on buildings at some point in the future. And I can imagine, you know, maybe it takes them 5 or 10 years to do that. And then maybe it takes 5 or 10 years for the industry to figure out, wait, there's a massive demand for timber. We better plant the trees. We better start building factories. So maybe in 50 years, we've got a whole lot of 10 times the processing capacity. Do you have any thoughts on how we might be able to advocate to speed that process up?
Well, it's all fairly obvious, really. I think that there have to be incentives, and there's got to be commitment. I just say a couple of things. One is that there are quite a lot of timber buildings are built with imported product. Not so much in New Zealand, but certainly in Australia, there are quite a number of like 10-story apartment buildings in Australia, lots of them, and most of them are made with wood from Europe. And the shipping, the energy cost of shipping is very low. So it doesn't, in fact, if you look at the Naylor Love calculator, you have two options there. You can use local CLT or imported CLT, and there's about a 10% penalty. But look, the job has to be done. There was an item in Stuff a week or two ago from Marty Berry, who owns Red Stag, and he was making, his argument was that the value of these carbon credits should go to the wood processors, which would allow them to invest more in wood processing. But on the other side, the counter argument to that is that the carbon is in the wood, and the wood processor doesn't actually own the wood. It's all sold. If anyone was to get the carbon credits, it should be the owner of the building. So I don't think that's going to happen in a hurry, but I think certainly if the demand is there, industry will come to the party.
Got a question through on the chat, just asking about are there any issues with building acoustics with CLT floors? I guess you could put fire into the same category. Any comments on those?
Yes, absolutely. I mean, one of the big benefits of wood, and if you compare wood with concrete, you use about the same volume, and the weight of the wood is 0.5 ton a cubic meter. Concrete is 2.5 tons. It's only 1/4 of the weight. And when you talk to your acoustic engineer, what do you want? Mass. Concrete acoustics is all about improving. So we have a problem if you just use a bare wood floor. So the buildings that we're working on at the moment, many of them have a floating floor. So they have a cradle and batten system with battens and a topping of plywood or fiber cement board. And then most of these buildings, the office buildings, they all have a suspended ceiling. You put some insulation in the suspended ceiling. So it's done. And in the latest building we've been looking at, with CLT walls, all of the walls are strapped and lined. So you don't actually see the wood. And that's done largely for acoustic reasons, but it's also makes sense because it's so, you then have a cavity of 50 or 60 millimeters where you can run all your wires and cables and things. So not a problem.
Andy, one common theme that's cropped up in conversations recently is the issue of standards. So that could be standards like putting emissions reduction standards onto various industries, or perhaps the development of New Zealand standards that kind of help support industry to make those changes. I remember back, I think it was probably over 2 years ago, we had Pierre Quenneville from Auckland University, who's involved in timber research there, and he'd just put the finishing touches on the draft New Zealand standard for timber, and it was with Standards New Zealand to publish, and it still hasn't come out. I guess that's an example of the fact that New Zealand doesn't have a lot of spare resources to pump into standards development, or at least it pretends it doesn't. Do you have any comments on how New Zealand's doing and whether it needs to raise its game, or what you'd like to see?
Look, I don't want to spend a lot of time on that, Brendan, but the good news is that the NZS 3603, the timber design standard, the current version of that is dated 1993, and I was the chair of the committee that prepared that in 1993. But the replacement for that is really, it's about to be released any day now, and finally, because Tobias Smith, who runs PTL, he's the chair of that committee. It is coming, but it's been arduous, and so standards are a problem, and I'm not going to go into it now, but we have to have standards because we need quality. The people are going to buy timber buildings, they want quality, and then we have to have quality. And I would just say that the problem really is that Standards New Zealand has never been funded properly. That's the problem. And so you've got volunteers, and often the only people who volunteer are vested interests. And so if the government was wanted to do something to actually enhance the building industry, it would be to put a bit of money into Standards New Zealand. That's all I've got to say.
Oh, that's been some very insightful comments on a whole range of subject areas there, Andy. We're probably just about time to wrap it up and let people go and grab their dinner, but does anyone have any last questions they want to throw in? No, well, I'm sure you'll all join me in thanking Andy. It's been a fascinating talk, and I'm sure that the video will also be well received by people who picked that up and view it who couldn't make it tonight. So really appreciate all your hard work in this area, Andy, and the insights you've shared tonight. I'm guessing that across the people on the call, there are a lot of people who will either be able to take action in implementing timber buildings, or advocating for government action in some of the, or industry action in some of the areas that you've mentioned. So we really appreciate being educated by your research and talk tonight. So thank you very much.
Okay, thank you. Thank you to everyone. If anybody's got more questions, you can email me. I'll be happy to talk.